Hi, I'm Cornelius Willis with the Google Cloud Platform team, and I'm so excited today because we get to talk to two eminent technologists at Google. First, we have Andrew Fikes, who is a distinguished software engineer at Google who is working on Bigtable and also the Spanner project, which we've published some papers about. And then Amin Vahdat, who is a Google Fellow and the technical lead for networking. And we brought these two folks together because the relationship between the services we provide on Google Cloud Platform and the capabilities, the underlying infrastructure, are really what define Google Cloud Platform as a whole. You can't really look at any of these things separately and understand really how they come together and provide something truly extraordinary. Some questions. So, Amin, you've said in public talks that computing is at a crossroads and that networking is going to define what computing is in the future. So why is that?
Yeah, that's a great question. I think it really is an exciting time to be thinking about the future of computing. We've been, to some extent, spoiled in computer science for many, many decades, where we would get basically free performance improvements every 18 months or so. If you wanted your software to run faster, all you had to do was wait for the latest, greatest processors to come available, upgrade your hardware, and magically your software runs faster. For the last few years, this has changed as we've now not been able to make individual processors faster, but we've delivered more of them. So the programming model has had to change. And the network is really the key enabler for bringing more and more servers together to work on bigger and bigger problems. So in other words, if I look at what we do at Google, we're bringing together hundreds, oftentimes thousands of servers together on individual computations. And it is the network that allows us to treat these hundreds or thousands of servers as one unit of computation.
I've heard you say that it's important to have balance between the different parts of the infrastructure, and you have to feed the processors. If you have all that processing capacity, you have to make sure that there's the network connectivity to give them data to work on.
That's right. And so one way to look at this is that servers need data to compute on. Just doing computation without any data is not very interesting.
Right.
And at Google, and I think at virtually any place that's interesting, the data is not local to a server. Right? It's not that there's no way that you're going to have the data that you need local to you. So any data that you're going to compute on is living across the network somewhere. And that's why it's so great to be working closely with folks like Andrew, because networking is about storage, and I think storage works very closely with networking. So if you look at a processor that can do billions and billions of operations every second, how do you make sure that you feed it data to keep going at that rate? Right? Otherwise, it's stalled waiting for the data.
So we build our own networking gear and our own networking software. Why did we start doing that?
A very simple answer. We couldn't buy for any price the scale and performance network that we needed to feed our processors. In other words, we had particular applications that we needed to run, starting with web search, but continuing across many different kinds of applications, and today to Google Cloud. We couldn't buy a network that would provide the capabilities that we needed.
Got it. So you're the global lead for storage services. How is your design and the services you provide different because of what we have in our network?
Well, building a global storage service is, first off, hard in some ways. And what Amin and the networking team brings to the table is they really take one of those really difficult problems off of my deck of things that I have to deal with. So oftentimes we're dealing with extremely large data sets, many petabytes. And as Amin mentioned, we're bringing that data together to sort of answer questions and compute over, and being able to take the network out of the equation, because I can depend on it to be there. I can depend on it to be really low latency. It means that I can make a lot of really interesting system design choices.
So it means that you're not spending so much time making sure the network is delivering bandwidth that you just assume it's there. You can design your services for very, very low latency, just make that assumption.
You can make that assumption, and it also opens up a whole set of interesting things that you can do. Amin talked about how we don't think about storage as being local. That means I can move compute from one node to another very quickly and access it with the same latencies. And this lets us work around hotspots in the data or machines going down, and allows us to recover things much faster.
Got it. So how is I know this is a huge question, I'm asking you to answer it ad hoc like this, but how is our approach to networking different from everybody else's?
Yeah, that's a great question, a hard question. I think it started with scale and speed. That was the simple part maybe 10, 12 years ago. But where we're at right now is also availability,
Right.
and what we call internally tail latency. So in other words, when you're doing distributed computation, you don't just care about how fast you can get at the data most of the time. Excuse me, in the average case, you care about how fast you can get at the data at the tail end of the distribution, of the 99th
So the worst
percentile.
case.
The worst case, exactly. So we design for availability, we design for security, and we design for predictability, making sure that the worst case is very close to the average case.
Got it. So a very narrow bell curve, a very narrow distribution curve. For
And that actually becomes relatively important. If you take a computation which starts and goes to one server and then collects data from 1,000 different servers, the probability that you find that sort of tail latency and it impacting your computation happens all the time, right? So you have to really plan for that worst case.
Right. So when a distributed operation, you send it out to many, many servers, it comes back and the last one in
Yes.
is the one that actually determines what
We
the
have to wait on
performance
all
is.
the data to come back in order to deliver a correct answer.
The design that I've heard you talk about in some of your talks is that we have used all this commodity gear and then centrally control it and use sort of centralized algorithms to determine what the actual connectivity of the network is. And so that's really different, right, from the way most people do it, right?
That's right. What's beautiful about networking as traditionally defined is that no one knows their role in the network. Everyone sort of self-discovers where they are. That's sort of the basis for the internet. One of the things that we saw at Google, though, is that we're building these data centers. We're building these data center networks, and how we connect all the servers together is predetermined. In other words, the roles and responsibilities of every switching element is known at design time. It's not something that has to be discovered or learned over time, as is the case with the traditional internet. So at Google, again, without really knowing it, we tripped upon the notion of software-defined networking.
And when was this, by the way?
This was about 10 years ago, is when it started. Now, software-defined networking has very specific meanings now, and it talks about particular ways of doing things, but the spirit in the end is that you have a logically centralized control over a very large-scale fabric. And that's what we wound up at. And frankly, we borrowed these ideas from storage systems. At Google, we always thought in terms of course, Andrew can say much more about this, that a storage infrastructure consisting of tens of thousands of disks is centrally controlled. So it was naturally for us to think the same way for how the network was going to be planned and controlled.
Right. But I mean, the argument that I've heard, and I don't know if it's a specious argument or not, but that having that central control also creates a liability and vulnerability.
It certainly can, but what we've found is that it actually makes the system simpler in the end, compared to a fully decentralized scheme. You do have the potential liability of a centralized controller, and that's why I use the fudge word logically centralized. We don't literally have a single point of control. It's just that we have relatively sophisticated algorithms based on systems like Chubby that we've published about in the past, Paxos-based leader election, that make it easy for us to build logically centralized control.
So Google is running its own private network connecting all of its data centers and all of its services. And if you're a Google Cloud Platform customer, you're on that private network. So is it different for you writing services with the understanding that that's a private network rather than being, connected over the public internet?
Yes.
How is it different?
I think in many ways we're fairly spoiled, right? We have a really strong team of operations people that are monitoring this network. It is the same network that carries our user-facing traffic of search, of Gmail, and other things, and so it is a resource that's incredibly precious to us, right? We spend a lot of time making sure that the capacity planning is done well, and that it performs as the specs say.
The bandwidth between our data centers is a real enabler for us, and frankly, we have more bandwidth between our data centers than many companies have inside of their data centers. And that really breaks down distance, where you can think of data that is across the data center as being almost local, but frankly, we can also even think of data that's stored in a different data center as something that we can go get as part of our computation in many cases.
So I've heard customers talk about this idea that they may be wherever their app is, wherever their customer is in the world, it's just like the customer is right there from a latency and a performance and customer experience perspective. It doesn't really matter where they're running.
That's right.
So I understand one of the statistics that's been thrown around is that we have bisectional bandwidth between 82 points in our network of 1 petabit per second. And I also know that the total bandwidth, aggregate bandwidth of the entire internet right now is some fraction of that, like two terabits per second or something like that.
200 terabits or so
200
is the
terabits,
bisection bandwidth,
right.
roughly.
So what's the right way to think about those two statistics? It's kind of crazy that Google has more bandwidth in its network than the entire internet does.
Well, so this is the distinction between local area networks and wide area networks. So one of our data center buildings will go to scale to about a petabit per second,
right.
And that allows all the servers within that building in aggregate to talk to one another at just enormous rates. Right. So the way to look at this is that you can transfer vast amounts of data among all the servers to one another. What is this driven by? It's the fact that computers can talk to each other much faster than people can talk to the network. In other words, what drives wide area network communication across the internet? It's people doing web search, it's people consuming videos. That actually, the amount of bandwidth required for that in the grand scheme of things is tiny compared to what the servers within the data center need to do to provide all that information to the end users.
Got it. So when I type in a query in BigQuery to hit a 3 terabyte table and it comes back in a few seconds, it's because of that bandwidth within that data center.
There's thousands of servers that are storing that data, and if we wouldn't be able to fit any that data on any one server, but even if we could, we'd run out of computation power on that server. We have to distribute it across thousands of servers for it to work.
Okay, so I understand we brought a switch from our data center. Can we go take a look at it?
Yeah, absolutely. Yeah.
Wow, this thing is enormous. What is this?
This is one small piece of a Jupyter network. This is what powers all the connectivity in our data center networks. It is called a super rack, affectionately within the group, and it is one stage in a multi-stage topology that connects all our servers together. So this is the middle stage. This connects all the servers, server racks to one another, below it at the first stage. And above it is yet another stage of networking that looks somewhat like this. Basically, data packets flow from the servers up through the super rack and then back down to other servers across the network.
Got it. So what's different here from what I might see in another data center that some of our listeners may have experienced in their data centers?
So when you buy commercial gear, you usually buy a single switch, and it might look a lot more glossy. It might have a lot more shine on it. It might not have all of the cables that are connecting things. Basically, what we're doing is we're exposing the fact that any big switch is composed of a lot of small ones. So if you were to zoom in here, what you would notice is that right over here is actually one switch. It's about 7 inches tall, and there are 8 of them in this column, another 8 in here. So a total of 16 switches in this super rack. Each one of these switches is a commodity switch. So they're things that anyone might buy as a standard top of rack switch. They're commodity, and they're driven by volume.
Okay. And so I noticed that we've got yellow fiber optic cables here, but also a lot of conventional copper as well.
That's right.
So how do those work together? What's the reason we have that?
So we have some black cables. These are the copper cables. Again, in traditional network switches, what you would have is a copper backplane. It would be hidden. It would be in the back. It would have copper traces etched on a piece of metal. And that would provide connectivity among all of the individual switching elements. Right. Here, we've chosen to expose that by using commodity switches. Again, commodity switches don't have the big backplane. So we actually provide connectivity from every switch to every other switch within the super rack. And those are the black copper cables. Copper cables have a limited reach, about the reach of this super rack here. If you want to leave the super rack, distances beyond a few meters, you need to go fiber optics. Okay? So these yellow interconnects are the interconnects that leave the super rack, either going to the higher stage of the switching topology or down to the server racks. Okay. So for example, the server racks would have also the other end of these yellow fiber optic cables that connect to the top of rack switch.
Got it. Got it. So how is this different from earlier generations?
We actually went along a number of different lines in building our switching infrastructure for modularity. And the software and the hardware is designed for being able to support upgrade in place across the data center. And that was really a key insight in that to be able to maintain availability of our infrastructure, we had to live with upgrading it continuously.
Okay, so the Google Cloud Platform that our customers are on today is constantly being upgraded and revised.
That's right. This is just one generation of our switching gear, one of many. And what we found is that both internally for Google products, from search to YouTube, no one can really tolerate taking down an entire data center for 6 months while we upgrade the entire infrastructure. What that means is that all of our servers must continuously run while the network is being upgraded from one generation to the next. And this super rack is a modular piece. Right? It is interchangeable with other super racks such that we can be upgrading one for another with no service downtime.
Okay, so this is not the be-all and end-all of Google networking.
Oh, far from it. So this was designed and deployed in about 2012. It was the 5th generation of in-house Google networking gear. You can imagine that since 2012, we've been working on subsequent generations, some of which has seen deployment in the data center now. And as we speak, we're designing the next generation of hardware and software that will go into the data center for deployment in 2016, 2017, and 2018. It's never ending to deliver the latest and greatest for Google's network.
Got it. So Andrew, a lot of atoms in one place here for a software guy, right?
Yes, absolutely. It's quite professional looking.
Great. So let's go talk more about the future. So that is quite a machine. Yeah.
Some switch.
Yeah. So what is that we're doing there is unorthodox or controversial? How is some of the designs we've put out there influenced the industry?
Well, that's a very interesting question. I think when we started down this path, many people thought that it just couldn't work.
Commodity switches.
Commodity switches, delivering the right levels of availability, the right levels of performance, but we thought it inevitable. In other words, if you look at the history of compute and the history of storage, it's followed similar trends. Network has just gone down that path most recently.
Got it.
Yeah.
Got it. So how are programming models, how are apps going to change? Programming models going to change? What does this mean further up the stack for people that are creating software?
Yeah, so I mentioned earlier, sort of as a programmer, as a system developer, being able to depend on the network to get access to my data. And I think what we've seen historically is steps to sort of disaggregate compute from data itself. And so this started with creating disks that were remote from where our servers were. We've been looking at disaggregating other types of storage recently, be it flash or upcoming NVRAM. And so what I think you'll see going forward is this much more of this programming model changes around being able to ask other nodes or other pieces of compute very quickly over the network to retrieve data and sort of bring it all together. And so from a programming point of view, it'll be as if your data is local, no matter where your compute happens to be.
Wow, so and it's taking the program wherever the data is almost.
It's taking the program wherever the data is. It also lets us sort of coordinate more effectively, right? So when you're thinking about large-scale distributed computation, you have a lot of trade-offs you can make, right? You might find that one server is slower than another, and you have the ability to go out and ask people really quickly and answer questions. And sort of super fast networks that you can depend on with low latency frees you up to try some of these more interesting techniques.
So the thing that occurs to me as we're talking about this is that the same kind of disaggregation that you're doing in the network space follows what we did in the compute space as well. And that rather than think about the data center as a collection of nodes, we think about it as one big computer. And networking and storage and even the distributed services that run on our infrastructure are all kind of designed with that same core idea in mind. It's the warehouse scale computer, as the paper says.
It really is the vision that we're driving after, is that you can think of the building as one unit of compute, one unit of storage, and one large switch that interconnects all of them together. And as Andrew was mentioning, you don't need to think about where your data is stored. It's available to you always. It's available to you really quickly. And in the end, convenient programming is being able to just reference your data, compute on it, generate the next piece of data.
Well, when you think about the day in the life of the average cloud developer today, more than half their time is spent just trying to make all this stuff work. Right? And if you take that out of the equation, think about what amazing apps people can write.
That's true. We spend a lot of time doing integration work, so bringing pieces of these things together. And at Google, we've started to think a lot about how programming models can change to sort of work around these sort of newfound latencies, these new sort of access route things, and how that actually changes how people develop applications.
So what's next for your teams? What should we expect?
Yeah, it's never-ending, the set of challenges. So I think certainly on the networking side, of course the networks are going to get faster, they're going to get lower latency. I think that for us, one of the really interesting challenges is how do we expose this all the way to the Google Cloud customer. In other words, we have fairly specialized and powerful programming primitives that we can deal with in networking environments. How do we securely and safely expose access to basically, if you will, bare metal performance all the way to the virtualized customers?
Productizing inside of Google. How about for your team, Andrew?
We've been doing storage at Google for a long time. I'm actually very, very excited about sort of our cloud customer workloads. They bring in new challenges for us, and they give us an opportunity to solve some really interesting problems. Amin mentioned earlier that our switches are developed and our networks are developed years in advance, right? It's a continually upgrade process, and so from a storage development point of view, we're already starting to plan for what the next networks will bring us, what capabilities it will actually unlock.
Right.
And so for us, we're starting to think about new tiers of storage and how we integrate those into applications and how they can actually, as Amin said, impact cloud user experiences, how we can make development simpler, and how we can make reliability, availability, and consistency of operations around storage be better.
Such exciting times.
Yeah,
this is the right time to be working on Google Cloud Platform. So thank you both. Thank you all for watching today, and go out and try it.